heat engines, refrigerators, entropy, and second law of thermodynamics. So today, and probably like the first half of Monday, we're most likely gonna be doing this, and then we'll do entropy, and then maybe the second half of Monday, we'll already be in chapter 21, electric fields, electric forces, and the topics will change quite a bit, okay? So we'll be on the electric fields, electricity the rest of the semester. So heat engines. So the idea of the heat engine is you're cooling a hot reservoir, you're cooling some heat and dumping some cold, dumping some heat to the cold reservoir, and then therefore doing work. So you have a hot reservoir, heat hot. So you're extracting heat from a hot reservoir, and here's the engine. Then you are dumping heat, you're doing some work. Then you're dumping heat into a cold reservoir, heat cold. See, so this is the cold reservoir. So the efficiency of the heat engine is defined as efficiency is defined as 100% times the work done divided by how much work you do divided by the input heat, Q hot. In other words, how much heat did it take to get the process going? That's the Q hot, and this is the work done by the engine. So that's the efficiency. And also due to energy conservation, we can say that first look at it, let's say like a picture. It's a general heat engine model. So you have QH, Q cold, and then you have to calculate the amount of work done by a heat engine, you say W is the difference between QH and QL. In other words, the work done is the difference of the two. So work, or the other way to say it, it would be to say this has to equal the sum of these two. QH is equal to W plus QC. Right? Or you could say W is QH minus QC. Now here's where the second law comes in, the entropy and the concept of the second law. The entropy measures the disorder of the universe, right? And second law of thermodynamics says the entropy of the universe always increases. So one statement of the second law of thermodynamics is to say you can never have a 100% efficient engine. You see, never have 100% efficient engine. So in other words, what that means is, if the efficiency was 100%, this would equal this. But in order for this to equal this, QC would be 0, right?
Is that a 2 in front of the C?
Which one?
Is that a 2?
Equals.
This one here?
Yeah.
No, sorry, the plus sign.
Oh.
So if the QC was 0, what would happen? In other words, if you can extract some amount of heat from a hot reservoir, right, and just do work from that, and not dump anything to the cold, you see, then you essentially created a 100% heat engine, because now you say all the heat that's coming, I'm gonna do valuable work with that. You see. So if the QC is 0, imagine Q0 is 0, you're still, in other words, what the first law of thermodynamics is the concept of energy conservation, right? So the first law of thermodynamics allows you to extract heat and do work without dumping, as long as you're conserving energy. So if this is equal to this, first law of thermo says, I'm okay with it. But then why doesn't that exist in the universe? Because second law of thermo says, oh no, you can't do that. You can't take this and do work and dump nothing. You see, you have to have QC, which means once you have QC, W is less than QH, right? Well, if W is less than QH, then the efficiency is less than 100, you see. So one way, let's just say, to visualize this, imagine the hot reservoir is a brick of like lead or something, lead cube at 80 Celsius. Then you have here, you bring with it ice at 0 Celsius. So bring them in contact, and of course heat will, this is your hot reservoir, right? So the hot reservoir doesn't necessarily have to be what we think of as an engine, like you're burning gasoline or something. It could be anything that is warmer than something else. In that case, this is your hot reservoir, and this is your cold reservoir. And when you bring them close to each other, what's gonna happen? Heat is gonna come from the lead to the ice. That's your QH. So imagine somebody looked at that and say, hey, while the heat is coming from the lead to the ice, let me devise something. Let me devise an instrument and put that instrument right in the middle between them. So some kind of machine or whatever you call it, some instrument. And then let me use that transfer of heat and then let this instrument do something as a result of that. Maybe test your blood pressure or something, you know. You use that source of energy as a way of that instrument doing something. They could devise something like that, you know. As soon as you bring something hot to something cold, you got something workable there. And you put something in the middle, and okay, now maybe that can test the thermometer, you could test blood pressure, or whatever you wanted to do. You could put some kind of an engine in between. But the second law of thermo says no matter what you put in there, you still have to dump some cold to the ice. You can't just say 100 joules of heat coming from the lead to the there. Oh, then the instrument is gonna give you 100 joules of production out of that. No. You still have to dump some heat to this. Of course, you got other issues too. To keep the lead at 80 after the lead is losing heat, you have to dump heat to the lead. I'm not even saying that, because what tends to happen? The lead doesn't tend to stay at 80, right? if the heat is coming, the lead's temperature is gonna cool. So in order for you to keep using the lead, you're gonna have to put more heat into the lead back from the other end, right? And then you're gonna have to put some, the ice is gonna tend to melt, so you're gonna have to kind of continually freeze the ice. That's why nobody has thought about this kind of an invention. So it ends up being maybe not that efficient. You have to keep the warm thing warm, keep the cold thing cold, and then put an instrument in between them and use it to do something useful, you see. If you could devise something like that, it could work, but you see the issues that are involved. But the second law is saying at least one thing, even if it, don't worry about keeping this warm, keeping this cold, forget about that. Even just putting an instrument there, if 100 joules of heat are coming, you can only do maybe 60 joules of useful work with it. The rest of the 40 you still have to put into the ice. That's kind of what it's saying. Okay. Now, if you reverse this process, you get what's called refrigeration. Or AC. So let's just look at the basic. Not that. Heat pumps or refrigerators. Cycle. I just want the basic flow. Yeah, this one. So basically, that's kind of reversed. So now you're taking heat from a cold, extracting that, putting some work in, taking cold from the cold and putting it into the hot. You see, that's the refrigerator. So imagine the lead example again. 80 degrees lead, and let's say ice at 0. So now if I reverse the process, imagine putting something in the middle, some machine in the middle, and then connecting it to electricity. So now I'm putting in the power, electrical power, putting it in between. Can I use that to extract heat from the ice and to continue to freeze the ice? In other words, extract heat from a cold reservoir by putting in energy. Yeah. See, so basically I'll reverse this process. I'm putting work in. I'm extracting heat from a cold reservoir. Right? From a cold reservoir, I'm extracting heat out. But can I do that without dumping heat to the hot reservoir? No.
No.
Second law of thermo says you have to put in work, extract some heat, but some of the heat you have to dump into the hot reservoir. Otherwise you'll be 100% efficient. So you have to dump heat to the lead. Which in that case is not a bad idea anyway, because that would keep the lead warm. It would keep the ice from melting. Yeah, but then why would you want to do that? What's the purpose then? I guess somebody can think of a purpose, right? Well, that's kind of what an AC is, if you think about it. Here's a room, then you have AC. Let's say on a summer day, the inside of the house is, let's say, 20, outside of the house is like 50 Celsius, Palm Springs, right? This is like the lid, you see? And this is like the cold. So I can take heat out and then dump it to the outside. I don't care that the outside is 50 and I'm making it warmer, because the amount of heat I dump isn't gonna change the temperature of the atmosphere that much anyway. Who cares? What matters to me is keeping my inside cold, you know? So that this machine that I'm thinking of has already been made, you know? Oh, God, goodness, when is this gonna end? Okay, how about a refrigerator? Refrigerator is a bit different than the AC, because this is the back of the refrigerator. Let's see here, cold. Oh, no, refrigerator is like the AC. The other one that I was thinking of is the heat pump. Oh, the heat pump isn't like this. It's like a heater. So on a cold winter day, the inside is 50. The outside is 20. Maybe it's cold, really cold, 5 Celsius. The heater puts in work, electrical work, takes heat in from a cold reservoir, and dumps heat to the hot reservoir. Oh, so a heater is opposite to the AC, essentially. The AC is making cold, colder, hot, hotter, but the cold is the inside of the house, you see. The heater is making the cold colder, but that's the outside of the house, you see. And then the warm, warmer. So the heater is opposite to the AC, but the same idea is that you're putting in work. In both cases, you're putting in work, you're taking cold, and you're dumping it into the hot. Except that the refrigerator and the refrigerator and the AC and refrigerator, your goal is to make something cold colder by taking heat from it. You see, AC, refrigerator, let's see there, yeah. Whereas the heater, this is the inside of the house. You want to make something warm, but keep it warm by dumping heat. So this is the inside of the house in a heater. So we define something called coefficient of power. I saw it a minute ago. Okay, coefficient of power for refrigerator and coefficient of power for heating mode. So the performance of a refrigerator and the heat pumps is expressed in terms of the coefficient of performance. So COP. So we don't call it efficiency. Efficiency is for heat engines, is work done over, so the efficiency is the one that I did for the the heat engine. The heat engine is like this. You have the engine, and then you have T cold, T hot, Q cold, work out. So this is the heat engine we first covered, and we said Q hot is work out plus Q cold. And then efficiency is defined as 100% times work out over Q hot. So for these ones, we call them coefficient of performance in the cooling mode, right? That's for the refrigerator, right? So then the desired output over the required input. So the idea is that we're dividing the output, what is our output desired, divided by how much we have to put in. The same idea is for the heat engine. We want to be able to do some work, that's the desired output. How much heat do we have to burn, put in, to get that done? So that's the idea of the efficiency. So desired output in here is what? How much heat do we want to extract from the inside of the refrigerator or the inside of the room? So you're saying desired output is the numerator divided by what do we have to put in? W. And then we've got the first law to say that W plus QC is equal to QH. Like this plus this gives you that. Okay? So now these coefficient of power for the heater, what do they call it? HP. And that's going to be what? Desired output over the required input. The desired output for the heater is QH. So that's, you're putting in hot to the inside of the room, which is already warmer than the outside on a cold winter day. So then you're doing QH over work in. But since QH is W plus QC over W, this cancels this, 1 plus QC over W, and then QC over W is COP. So then that means COPH is COPC plus 1. Coefficient of performance of the heater is always going to be 1 plus the coefficient of performance of a refrigerator or cooling. Okay, so they're always going to be 1. So in other words, if you take the same engine and reverse it, and now use it as a refrigerator or versus a heater, the heat in the heating mode is going to be better performance. You see? Okay, so if you look at this website, it's saying The term coefficient of performance is used to describe the ratio of useful heat movement per when used for heating a building with an outside temperature of, for example, 10. A typical air source heat pump has a coefficient of performance 3 to 4. Okay, if the outside temperature is 10. So remember this one, heat pumps for heating, they're used when it's cold outside, of course, and when it's warm outside, it extracts heat from the cold outside and then dumps it into the warm inside. So the coefficient of performance is 3 to 4, this one here. So if you took that same exact machine and just reversed how it's functioning and made it act as a refrigerator, it would always be 1 less than its coefficient of performance in the heating mode. So typical coefficient of performance. Now let's see, yeah, even this other website says 3 to 4. Industrial heat pumps, let's see what they're at. Oh, okay, you see that? This graph. Kind of see, depending on the temperature of the inside and the outside, what the coefficient of performance is going to be. So it tends to range from about maybe 7 all the way up to potentially 14. You know, so okay, I'll show you later how to do that too. Okay, now let's go to actual particular cycles and talk about, oh, you know what, this was a good problem. You could do this as a good warm-up. This one's, what is the coefficient of performance of a refrigerator? Oh, you know what, we haven't talked about. Okay, you know what, let's go to talk about the Carnot cycle. So in heat engines, one of the classic cycles so of course we've got this different kinds of heat engines. So there's cycles, there's engines that run on phase change cycles. In these cycles and engines, the working fluids are gases and liquids. The engine converts the working fluid from a gas to a liquid, from liquid to gas, or both, generating work from the fluid expansion or compression. Rankine cycle, classical steam engine. Regenerative cycle, organic Rankine cycle. So in those ones, there's a phase change that's occurring to the liquid and the gas. Then you get the gas-only cycles. In these cycles and engines, the working fluid is always a gas. There is no phase change. So you got the gas only. Those are phase change with liquids to a gas. So you got the Carnot cycle, Ericsson cycle, Stirling cycle, the Stirling engine, internal combustion engine. So it's kind of nice to see the list. Carnot cycle, Ericsson cycle, Stirling, Otto cycle, and then diesel, Atkinson's like Atkinson diet. Then you got liquid-only cycles. In these cycles and engines, the working fluid are always like liquid. Stirling cycle. But it appears that Stirling Looked like it appeared twice. Stirling engine, and then there's another one, Stirling Malone engine. And then you got electron cycles. That means it's more electrical cycle. Johnson thermoelectric energy converter, thermogalvanic cell, thermionic emission, thermotunnel cooling. You see, so there's engines that run on electrical power, right? And then there's magnetic cycles. Thermomagnetic motor, Tesla. Is that the Tesla car? Oh, the Tesla designed that, I guess. Okay, so the classic one to start with would be Carnot cycle. First thing to do before even reading anything like this is to look at the PV diagram of a Carnot cycle. Where was the PV? I think we just passed it. Yeah, it's this one. See here, it starts here. You could kind of start them anywhere, but it starts here. Goes isothermal, adiabatic, isothermal, adiabatic, right? So remember, adiabatic, you go from one isotherm to down to a different isotherm. Then you stay in that isotherm, then you go adiabatic. So it's isothermal, adiabatic, isothermal, adiabatic. That's Carnot engine. So for now, let's talk about the cycles, what the steps they include, and what their ideal efficiency will be. You see, so the Carnot cycle. So it starts here. V1, P1, T1. So we're gonna go isothermal. Beautiful, I love these graphs. T2 is going to be the same as T1, and you're going to drop to a different temperature. So this is going to be V2, this is going to be V3, this is going to be T3, and you're going to go back up, right? This is going to be V4, this is going to be T4, this is going to be P4, this is going to be P3, this is P3, P4, right? T4, but T4 is going to equal to T3. Then you're going to go back up adiabatic. So in the first stage is isothermal, heat is coming in, right? Q in. Isothermal. How much heat is coming in? Q into the gas. It's delta E plus the work done by gas. But remember, delta E was 0 in isothermal, right? So, and then the work done by a gas in isothermal was what? nRT ln of V2 over V1, right? So then the Q in is going to be nR, and then it's going to be T1 ln of what? V2 over V1, right? That's going to be the heat in. That's it. Now, in the second stage is adiabatic. So this is isothermal. Second stage, adiabatic. In adiabatic, Q is 0. So there's no heat exchange. So then what's left? Then you just have delta E plus work done by gas is 0. Oh, the only thing we know is that the temperature that it achieves here, okay, what was the equation? P2 V2 to the gamma is equal to what? P3 V3 to the gamma. Okay, so then what's the work done by the gas during this state? We have to do the integral under the PV diagram, right? Work is integral PdV. P is equal to, remember during this state, PV is a constant. PV to the gamma is a constant. That means P is equal to a constant over V to the gamma. But then what's that constant equal to? That constant would equal to whatever the value of the pressure here, whatever the value of the volume there to the gamma power, right? That means it's staying constant throughout that process. So it'd be P, the constant would equal P2 V2 to the gamma. Or you could say P3 V3 to the gamma. So in other words, whatever pressure, whatever temp volume it has there to the gamma, that stays constant. You see? So then we could say here, constant is P2 V2 to the gamma, and then dV over V to the gamma, and then the limits of the integral are V2 to V3. The integral of that is what? V to the negative gamma plus 1 over negative gamma plus 1, V2 to the V3. So the work done during this, we'll call this work done in the second state. Work is equal to P2 V2 to the gamma. And I put V3 into this, so you have 1 over negative gamma plus 1 over V3 to the gamma minus 1 over V2 to the gamma minus 1. And then I could switch the order of this and switch the order of that. So I'll have W2 is P2 V2 to the gamma 1 over gamma minus 1 over V2 to the gamma minus 1 over minus 1 over V3 to the gamma minus 1. And now the work done by the gas is just simply going to equal negative delta E. Negative delta E2 is just going to equal negative of the work done. So it's just going to be negative of this. Okay, so that's going to be the delta. So in each stage, we are writing the Q into the gas. This is Q1, we'll call this. Yeah, so let's get in the practice of writing it this way. In each stage, write down the heat into the gas, the work done by the gas, and the delta E of the gas. So in the first stage, delta E1 was 0. Q1 is this, and W1 is the same thing as Q1. So it's going to equal nRT1 ln V2 over V1. So if you get in the habit of that, Q1 delta E1 W1, and now we say Q2 is 0, and then W2 is this, and then delta E2 is this. That way you get organized with all your steps, right? Now in the third stage is gonna resemble the first, right? So, except now you're going backwards. You're going this way, you're compressing the gas. So then, delta E3 is gonna be 0. And then Q3 is gonna equal what? You can kind of follow that same idea, right? NR T3, because that's the temperature here. It's isothermal. ln of what? V4 over V3. And of course, if you put that, you're gonna get negative because V4 is less than V3, right? This is a smaller number than that. So that means heat is actually coming out of the system. Okay? And then what's the work done? The work is the same as the Q3. So the W3 is NR T3 ln of V4 over V3. So delta E3. And then the fourth stage is gonna resemble the second. So if some of this you can kind of do by guessing, you don't have to redo it from the beginning, right? Fourth stage is gonna be what? Q4 is gonna be 0. W4 is gonna be what?
P3V3.
P2V2, P2V2 is P3V3. So now it's gonna be P4V4 to the gamma, or I could do P1V1 to the gamma. So I could replace this by P4V4 to the gamma. And then V2, instead of V2, it's gonna be
V1?
yeah, it's gonna be, let's see, V2 is the, from here, this. So it's gonna be, it's from V2, I replace it with V4, and then V3, I replace it with V1, yeah. So it's V4 to the gamma minus 1 minus V1. In other words, V2 is the beginning volume of when the adiabatic starts to the ending volume. So here the beginning volume is V4 to the ending volume. Okay, so then that's it. And that's W4. And and what else do I need? Oh, the delta E4 is just gonna be similar to this, right? Negative P4V4 to the gamma. Now, what should happen if I did it right? If I add up all the delta E's, remember we did a complete cycle on Monday? The delta E's should all add up to 0. I should come back to the same state, right? The delta E's, no matter what cycle you have, it should always add up to 0. So that means delta E1 first is already 0. So I only have delta E2 and the delta E4. They should cancel. Is that, let's see, is that true? Delta E total. So it's gonna be negative P2 V2 to the gamma, 1 over V2 to the gamma minus 1, minus 1 over V3 to the gamma minus 1. Okay? And then if I add the delta E4, obvious that it cancels? It's not too obvious, we probably have to put some more work in to show, but it should be equal to 0. Let's see here, negative P2, if I distribute this in, what do I get?
But
P2?
P2, V2 is equal to
Oh yeah,
P4.
because if you divide this by this, you get what? Negative P2, V2?
Huh?
Don't the gammas cancel? Oh yeah, you just get negative P2, V2 if you distribute it in, right? The gammas cancel. Plus P2, oh this one doesn't cancel. V2 to the gamma over V3 to the gamma minus 1. Okay, then if I distribute this in, negative P4, V4, and plus P4, V4 to the gamma, over V1 to the gamma minus 1. Well, this one you could say is P2, V2 is nRT2. And then that one, nRT, this is P4, V4 is equal to nRT4. It's probably gonna take some more work. P4, V4 to the gamma, P1, V1 to the gamma, P2, V2 to the gamma. I know it's gonna happen, but it's probably gonna take several steps. What we have, the governing thing that we have is that we have P1, V1 to the gamma is gonna equal P2, V2 to the gamma. That we know. We know P3, V3 to the gamma is gonna equal P4, V4 to the gamma. Oh no, sorry. P4, V4 to the gamma is gonna equal P1, hold on.
No, P3.
Yeah, from here to here is adiabatic. So P4, V4 to the gamma is P1, V1 to the gamma. Then from here to here is isothermal, so we have,
P1.
did I say this wrong?
P2, V2. P3.
Huh?
For the first one.
Oh no, yeah, it should be P2 to V3, hold on. P2, V2 to the gamma is P2, V3 to the gamma. Did I mess that up in the earlier? No? Okay. So P2, V2 to the gamma is P3, V3 to the gamma. Then you have P4, V4 to the gamma is P1, V1 to the gamma. And from here to here is isothermal, so you could say P1, V1 is equal to P2, V2. That's isothermal from here to here. And from here to here, P3, V3 is P4, V4. That's isothermal. So all these are your restrictions. So prove that this is 0. Okay. It's probably doable, but it takes some work. P2, V2 is P1, V1. Okay, anyway, let's just say it's 0. That's accepted.
Can you do that on the exam?
Don't want to go down that rabbit hole. it should be 0.
You could just say it goes to
Okay,
0.
but now let's calculate the efficiency of a Carnot engine. What's gonna be the efficiency? It's gonna be the total work done by the engine. That's probably more important than proving delta is 0, because I know I did it right. Yeah, gotta be right. Okay, so the total work done by the gas divided by the heat into the gas. That's the efficiency.
On
So
the
which
test, can
one?
we cross it out and assume 0 too?
Which one?
On the test?
No, on the test, you're gonna get numbers. And when you get numbers, you better make sure that at the end, when you add them, you get 0. Yeah. So now the efficiency is gonna be, how much, where did the heat come in? Well, here, heat came in, and here, you dumped it. Right? So the heat came in only in the first process, right, first stage. So then there is the work done by the heat in. So then what's the work done? Then that's gonna be the sum of, oh, dang it, now we have to add these two works. Well, did we do work in the other states? Oh, man, we have to add all of them up.
Yeah.
But look, if the works cancel, if the delta E's are supposed to cancel,
Then that works too.
and the works are gonna cancel, so gone. So we only have to add this work, right? Plus this work, which is gonna be negative, right? The gas is doing negative work when it gets back.
And it's the same.
Divided by the heat in stage 1, which is this one.
Isn't the same values?
Well, the heat in this case happens to be the same as the work, the W1. It's not always gonna be the case, but in this case it is. So then we're just gonna do 100%.
2 times.
This is gonna be nRT1 ln of V2 over V1 plus nRT3 ln of V4 over V3 over, and then nRT1 ln of V2 over V1. NR cancels. T1 ln of V2 over V1. It should get even simpler. Hold on, let's see, V2 over V1 is, because we've got V2 over V1 is the same as V3. I believe, let's see here, V3. I believe the ratio of V2 to V1 is going to be the same as the ratio of V4 to V3. It's not a simple proof, huh? The ratio of this to this is the same as ratio of that to that. Graphically, it does look like that. V2 over P1 is gonna be V1 over V2. Oh, okay. To the gamma minus 1, V2 to the gamma minus 1 over V1 to the gamma minus 1, V4 to the gamma minus V3 to the gamma. Oh, okay, I've unlocked it. Dang, it's like a puzzle. So I've got V4 to the V3 is equal to V2 to the gamma minus 1 over V1 to the gamma minus 1 times V4 to the gamma over V3 to the gamma. Then you get V4 over down there. You get V4 to the 1 minus gamma over then V3 over there, so V3 to the 1 minus gamma is equal to V2 to the gamma minus 1 over V1 to the gamma minus 1. Right, so basically that proves that the ratio of, if both of these powers are the same, that means the ratio of V3 to V4 is the same as the, except this is inverse. So it is the same as the ratio of V2 over V1. No, it should be the other way around. I made some mistake. So, in other words, this one here divided by this one should be the same as this one divided by this one. V3 to V4. V2 to V1 is V3 to V4. V2 to V1. Yeah. Oh no, it is right. I did it right. Yeah.
Surprise.
Wow. Wow. So that means that's actually the thing that probably cracks this whole thing. That could have been used earlier to show that the delta E was 0. Yeah, that was the missing puzzle. You had to prove that this over this is the same as the ratio of this to this. And it took some work. Okay, now that could be proved to go back to the work now. If this to this is the same as this to this whole thing cancels. Therefore, the temperature of a Carnot engine only depends on the temperature of the reservoirs. This is Carnot. Sadi Carnot proved this back in 1830. Carnot engine. He did all of this proofs in 1830. So T1, except this is negative, right? Have you seen that equation before? Yeah? Where the Carnot cycle temperature, the efficiency depends only on the temperatures. So this is called Carnot efficiency. Oh yeah, it was in the lab, wasn't it? Last week's lab.
It was?
That's why I said don't turn in the lab today, because I said you're gonna understand it better. Now you understand it a lot better. I will understand it. I probably confused the hell out of it even more.
It isn't for sure guaranteed something. I will take the whole test if they really like this one question. He lost me after he was finished drawing. Alright, bro.
Carnot, ideal Carnot efficiency. T hot minus T cold over T hot. Yeah, T hot minus T cold over T hot. Now, if we ran this cycle backwards this way, you go down, you go this way, you go this way, you go this way, it turns into a AC or a heat pump. So you extract heat from the cold reservoir, you end up doing the net work, you're putting in the work, and then you dump heat to the hot reservoir. So if you're using this as a refrigerator, this would be the inside of the refrigerator, right? And then you would be extracting heat from the inside of the refrigerator. This would be the back of the refrigerator, and you would dump heat to the kitchen. You see? That's why the kitchen gets warm. The back of you're dumping heat through the back of the refrigerator, right? And if you're dumping and using this as a heat pump or as like a heater, this would be the outside air, and then this would be the inside of the room. So you're dumping heat to the inside of the room, making it hot. So what would be the coefficient of performance then? We don't have to rederive it. It's, what do we do here? So once you're able to derive the equation for the work, what's coefficient of performance in the heating mode? And what's coefficient of performance in the cooling mode? This is the heater, this is the refrigerator. Cooling mode is the refrigerator, and the heating mode is the heater. So that would be what? What was the equation? QH over, so what you're interested in, over what you are putting in. So then what would that be? This is the heat that you're putting in, right? This one. So now that becomes the heat that you're putting it into the room. So this goes to the numerator. You know what, we don't need all this nRT1 because we already know the ln's cancel, so that this just goes to the numerator. And then the work in is gonna be what? This one right here. Except it's instead of T1 minus T3, it's gonna be opposite. T3 minus T1. Let's see here. No, this is the hot, T1 is the hot. This is the cold. No, I should have a T hot. Yeah, I should have it like that. So basically this one goes down, this one goes down, this one goes up. And then you have here, this one goes to the bottom. Okay, so basically the inverse of this. Okay, how about coefficient of power in the cold? The difference with that one is, that one you're using this heat, not that heat. So I believe the only difference is that here is T3. Okay, so this is the coefficient. So you could take the same efficiency that you got for the engine, reciprocate it, and then get the equivalent coefficient of power in the heating mode. Have you guys seen the Stirling engine? Maybe in the engineering class with the median, right? Have you guys, who's taken that class where that you make a Stirling engine? So what is the cycles of the Stirling engine?
Forgot. It's been so long. Let me see.
Stirling cycle. Looks a bit simpler, not as complicated. It's a constant volume. I'm just not sure is this isothermal or adiabatic? Well, let's read it. Isothermal heat addition, isochoric heat removal. So here you're adding heat, you're removing heat. Here isothermal, compression, okay? Could we derive the equation for the efficiency? Huh? But you know what? It's simpler than adiabatic because we don't have PV to the gamma to worry about. Right? So what changes? Well, first cycle is the same, right? Is this isothermal? First cycle is the same, the third cycle is the same. Don't reinvent the wheel, right? So then, what's the first stage gonna be? Same thing? So let's just do Stirling because it's kind of similar to Carnot. And then we could do some of the other ones on Monday. Stirling. So it's isothermal, isovolumic, isothermal. And we call them the same thing again. P1, V1, P2, V2, P3, V3, P4, V4, you know. Then this one will be Q1 is nRT1, LNV2, so that one stays the same. Delta E1, that stays the same. Okay, now how about second stage? Actually, we did the brutal one first. All right. Second stage is isovolumic. So what's the work done? Isovolumic. W2 is just 0, right? So in this stage, what's the heat into the gas? So the heat into the gas is equal to the change in internal energy of the gas, because the W is 0, right? And then what's the change in internal energy? NCV delta T, right? NCV delta T, and then delta T is going to be the temperature it has here, so we'll call this T3, T2, this is T4, T1, right? So then it's just going to be the T3 minus T2. So this one, heat is coming in. This one, your heat is coming out. Because that's going to be negative, right? Okay, how about the third stage? Okay, third is going to be like the first. Okay, and then the fourth is gonna be like the second. So which is gonna be W4 is gonna be 0, Q4 is gonna be NCV delta T. So NCV T1 minus T4. So you're dumping heat here, and you're adding heat here. Q4, Q1, Q2, Q3. So what's the efficiency? We want to cheat, they probably have an equation. So you see, they're running a simulation of a Stirling engine. See, constant volume. You go down isothermally. Then you dump heat to the cold reservoir. Oh no, hold on. Now you dump heat to the cold reservoir. You expand. Then you go down. Heat comes in from the hot reservoir. So that's this guy. Then you go up. Then you dump heat this way. You see? Then you go back this way. Then heat comes in. See, cool? Simulation of that.
Wait, how does heat come in this way? Are you cooling it down?
No, I did the wrong. This heat's coming this way.
So
Like
then when you
this.
open up, you're cooling it down, right?
Yeah, you're warming it up. Then you see when you're going this way, you see it's opening,
Yeah.
then you're dumping this way. That's this one.
Oh, okay.
It's cooling.
So you're dumping it out of the system.
Yeah.
Okay. Okay.
Okay, it's kind of the efficiency. What is the efficiency? Efficiency or Stirling. Yeah, it looks like the total work is gonna be that. Okay, so yeah, I get this is a nice one too, good simulation. This is another one. I think in that class he has you guys actually making it, the different versions. So what's the efficiency then? It's gonna be the total work done. So W1, there's no W2, there's no W4. W3 is just gonna equal that. So it's gonna be nRT1 ln V2 over V1 plus nRT3, right? No, am I looking at the, no, I was looking at the wrong one. The work done is this one. No, it is still the same. nRT1 ln of V2 over V1. This work is 0, this work is the same as that. Okay. nR plus nRT3 ln V4 over V3. Okay, divided by the heat into the gas, which is this and just this. Right? So it's actually the, isn't it the same thing?
Let's just Q. Wait, what?
It's just this guy, so it's this guy.
And Q4. And Q4.
Oh, instead of this guy, it's this guy. Oh, that's why it's so different. Oh, okay. NCV T1 minus T4. NCV T1 minus T4. Let's see here. We should do it so that it's positive. Yeah, this is a positive, this is a positive. Those are the heat coming in. So the N cancels. Is that the only thing that cancels? CV depends on if it's a, oh, I see C, yeah. So that means it depends on if it's a, let's say it's a monatomic gas, so it'd be 3/2 R. Right, so then R would cancel, and you'll be left with what? Can we say V4 to V3 is same as V2 to V1? V2 to V1, V4 to V3? Except they're, yeah, they should be the same. Actually, wait a minute, V4 is the same as V1. And then V3 is the same as V2.
Yeah.
Yeah, of course, except this should be negative of that, right? So then it's just reverse. So actually, oh, but it doesn't cancel, right? So we have T1 ln of V2 to V1, and you're gonna have minus T3 ln of V2 over V1. I'm just gonna replace with this with V2 over V1, but change the sign, over, they'll cancel the R, T1 ln of V2 over V1 plus 3 halves T1 minus T4. I don't think we can even simplify it. T1.
We can say same volume.
It seems like on a Stirling engine, the efficiency depends quite highly on the ratio of the volumes. Whereas in the Carnot cycle, it doesn't really matter. As you could have something like this. You could have something like this, bigger. You could have something like this, huge. Of course, this would do more work than this, but you would have to put in more heat into this guy. You see? So for the Carnot cycle, the efficiency only depends on the temperature of the hot and the temperature of the cold. You see? With the Stirling cycle, not that easy. It depends on the temperature of the hot, the temperature of the cold, but also depends on the ratio of the volume. So the more you make the ratio of the volume, in other words, the Stirling engine that's like this, is gonna be a lot more efficient than a Stirling engine that's like this. Not only does this one do a lot more work, it also does more work more efficiently. When the ln is bigger, when this guy is big, and the numerator has 2 of them, versus the denominator has only 1 of them, you see? So when the volume ratio is bigger, it gets more efficient. So with Stirling engine, you want a bigger volume difference. With Carnot cycle, it doesn't really matter. You see? Okay, so on Monday, we'll see other different examples of engines. Okay, good job.